Hi, my name is Jenny, and I am introducing the background information. Skin injuries are among one of the most common injuries to the body. To prevent further damage or to limit the possibility of infection, the wound is often cleaned and dressed with gauze. However, if the gauze is applied at a joint, for example the elbow, the patient would experience discomfort every time he or she uses the elbow. In addition, traditional wound dressing must be removed in order to clean or apply medication. The bandage itself is unable to release drug molecules to treat the wound. This particular study aims to create a self-healing hydrogel that can be used specifically for the joints to minimize patient discomfort. Naturally, the next question is, what has been done in the past about this? First, to create a self-healing hydrogel, the environment must be optimal. The first group mentioned in the slide created a hydrogel with high water content. In turn, this increased the presence of oxygen and helped maintain an optimal healing environment. The second group mentioned created a hydrogel that provides scaffolds for rapid cell migration. This is especially important as the study reported that cells incorporated during the scaffold formation proliferated and formed extensive 3D networks within 48 hours. Also, there has been hydrogel research conducted to address the needs of wound dressing of joints. To do so, researchers developed highly flexible strain and pressure sensors in order to detect joint motion. What is this particular study doing that's unique to their study? First, they're combining a Schiff base and copolymer Michel cross-linking into one polymer, which is a formulation, as they stated, that has not been used. Their particular hydrogel will be suited for physiological conditions due to its ability to inhibit bacterial proliferation, promote pH-dependent biodegradation, and create a comparable modulus to human skin. It also demonstrates self-healing ability. As a bonus, the hydrogel has the ability to incorporate drug molecules into its structure and be released over a course of time.
This is Jillian Tettebaum with the Methods section. Overall, the authors wanted to create a hydrogel with and without capsaicin and did various tests to ensure that it would work correctly as an alternative wound dressing. They then performed a one-way ANOVA for significance. First, the authors created the hydrogel. They created QCS solution and PF127-CHO to be used as a cross-linker since it was known to be biocompatible and formed micelles. This was confirmed using H&MR spectra. They then created curcumin-loaded hydrogels by varying the molar ratios from 0.8 to 1.3 of PF127-CHO that was dissolved in the PBS buffer solution. They then recorded the gelation time using the tube inversion method. The authors then wanted to test the physical properties of hydrogels. They used various methods to investigate the chemical and physical properties as are listed on the slide. They then assessed the self-healing performance by macroscopic and quantitative self-healing tests, the mechanical properties as seen in Figure D of the hydrogel without capsaicin by uniaxial tensile tests for tensile stress strain, and the compressive and recovery properties with a rheometer. The authors also wanted to assess the healing properties of the hydrogels since they were being used as a wound dressing. The pH values of the PBS varied from 6.0 to 7.4 to evaluate in vitro drug release of the hydrogels with the cross-linking densities mentioned before. They then used the method of scavenging free radicals to evaluate the antioxidant efficiency. They used E. coli and S. aureus to test the surface antibacterial activity, a full-thickness skin defect as well as female Coumadin mice to evaluate in vivo wound healing, and histopathologic examination and immunochemical staining to evaluate epidermal regeneration and inflammation. Lastly, the authors tested the biocompatibility properties of the hydrogels. They tested the adhesive ability to host tissue using fresh pig skin, the hemostatic potential with cross-link density 1.0 in hemorrhaging liver mice to make sure that blood is clotting correctly since it'll be used as a bandage, and the cytocompatibility of hydrogels without curcumin by directly contacting the hydrogels and mouse fibroblasts since fibroblasts are important in wound healing.
Hi, I'm Emily, and I'll be talking about the results from this paper. Before I delve into the specific figures, I'll preface the results by saying that the main findings were network stability and similarity to skin even under fatigue, fast and reliable self-healing, both positive antibacterial and cytocompatible behavior, and antioxidant ability with the inclusion of curcumin. Figure 3 shown here is all about the mechanical testing performed on the hydrogels. There is a lot going on in this figure, but the most significant results are B, showing stretchability of 76.1% to 58.2%, which is in line with joint bending. C, showing moduli of 21.5 kilopascals to 37.3 kilopascals, which is also similar to skin, which helps ensure the integrity and adhesion during healing. Part E, showing that increasing the crosslinker concentration, QCS-PF, gave higher Storrs modulus of an elastic response. And then parts G and H, which showed that at 90% compression strain for 50 fatigue cycles, there was some plastic deformation, but none at 60% strain, indicating good resilience and fatigue resistance in the hydrogels. Figure 4 shown here illustrates the self-healing abilities of the hydrogel. Parts A through F demonstrate that the hydrogels, when cut, can self-heal and maintain that healing with the force of gravity applied, and parts G and H show that this healing occurs on the timescale of as little as 3 seconds. Parts I and J show that the intersection of the storage, aka elastic, and loss, aka plastic moduli, was at 113.7%, meaning only at that level of strain does the network collapse. Below 113% strain, it exhibits immediate self-healing consistently. So, the hydrogels can withstand quite a lot of strain and reliably heal. This figure shows the hydrogels are antibacterial in parts A and B, because all of the formulations killed greater than 90% of E. coli and SRS bacteria. And in part D, cell proliferation in all formulations was also similar to the control over 3 days, indicating good cytocompatibility as well. Finally, it was found that the antioxidant curcumin could be effectively released from the material. In part A, it is shown that increasing QCS-PF pH leads to a decrease in antioxidant release concentration and release time. And part B uses DPPH to test curcumin delivery, showing that increased amounts of curcumin containing hydrogel led to increased DPPH scavenging, or aka decreased absorbance, which is correlated to effective delivery.
Hi, I'm Yash Lahoti, and I'm going to be talking about the discussion section. Before we move on to talk about the overall impact, it's important to address whether or not our hydrogel meets the specific criteria necessary for an ideal wound dressing. From this research, we see that this hydrogel has antibacterial properties. It has resilience to abrasion and deformation given its self-healing properties. This hydrogel does have an extended drug release, given that this research used curcumin as the drug, and it does have an acidic pH response, which is the condition that is most likely seen in injuries. Furthermore, this hydrogel does also possess adhesive properties, which is necessary to keep the hydrogel fixed in location. And we do see accelerated and active wound healing from the application of this hydrogel. So now, what are the next steps? So before we can continue and bring this hydrogel to market, we need to first vary some experimental conditions to get a full-scale understanding of how this hydrogel will interact with the human body. First will be to modify the drug content and potency. Given that this study simply used curcumin, we could potentially alter the drug and vary these drug concentrations to see how they could affect the overall wound healing. Furthermore, we could test various injury models that are not specifically located to the elbow and view the hydrogel's performance. Furthermore, the human body is exposed to various environmental conditions, so testing these will also be important. The overall impact is that this hydrogel does result in accelerated wound healing, and given these properties that we're seeing and the overall benefit, it's likely that the study will now move to clinical trials to see how this will now interact with the human body. And finally, as this hydrogel, we would like to see this as a replacement for the Band-Aid, as a new standard for an active wound dressing and wound healing process.
Some possible limitations to this is that on the skin, everyone's flora is different. Sure, a group of common bacteria can be found, but I'm hesitant to say that its antibacterial property can combat any antigen attack. After hearing how the hydrogel is made, I am also worried that this is expensive, and I wonder if it can be accessible to the general population. In addition, this research study mostly addressed wound dressing for joints, which is very specific. The research looks promising, and I would like to see how these hydrogels be used for deeper wounds, particularly ones seen in mass casualty situations or in military war zones. The hydrogel's antibacterial properties are particularly useful to prevent infections and worse wounds, but again, it should be tested in a variety of environments similar to human skin.
Overall, this research appears very promising, although it is somewhat of a niche problem since it's only being applied to joint wounds currently. I could see it generalizing to different wounds due to its high biocompatibility and acting more or less like skin. I am surprised that it wasn't tested with pathogenic bacteria on the skin, since I would think that this would be the main concern for infection. I'm also surprised that they didn't use a more common antibiotic, instead opting for curcumin. I feel as though a more common antibiotic would be a better application of this, and I assumed that if this were also being tested, that would be a better alternative.
The results of this study are promising for the issue being addressed. Though it is specific to joint wound dressings, I think it could be adapted well for different applications by releasing different drugs or differing the material strength or cross-linking. Building off of that, I'm interested to see how the hydrogels perform with different types of molecules to release. Only one type of molecule was tested in this study, and I'd like to see how both large and small molecules and biologics perform. On a more commercial end, I would like to see how the manufacture of a product like this could be scaled beyond a laboratory environment. Clearly, there is excellent potential for commercial application, and I'd like to know more about how the physical creation of these gels could translate and be scaled up.
While this hydrogel was extremely effective in acting as a wound dressing, I think that this can be taken a step further, given that there is a potential for this injectable hydrogel to have an application for to address deep wound injuries. It's going to be interesting to see whether or not this is going to be a more commercial route or as a post-surgical treatment that's specifically only used in hospitals. Another great point is the versatility that this hydrogel has with drug release, given that these drugs can be modified and can have a more active process than curcumin. But there are some limitations. First is going to be that this hydrogel is likely very expensive and inaccessible to the general population. Second is going to be that mouse skin, which is the model that is used for testing this hydrogel, is not a perfect model to address wound healing in humans, given that there is a different mechanism. So only clinical trials and application on humans will be able to test whether or not these properties uphold. And finally, while this hydrogel does have antimicrobial activity, it's important to measure this and expand this to a broader range of pathogens, given that the human body is encountered to various conditions, and knowing the resistance in all of these broad range scenarios is important for preventing infection and effective wound healing.